Ms. Irina, can you hear me?
Yes, sir, I can hear you.
Okay. So, okay. So before that, what I was discussing was about. Just 1 minute. Yeah. So I was saying that the dependence can be overcome in two different ways. Either you maintain the dependence by avoid a hazard, or you eliminate the dependence by transforming the code. Right. So the second point is to eliminate the dependence by transforming the code, which is a difficult thing to do because you might not get a different way to write the same thing. So the prime way is the first one where we maintain the retain we let we let the dependencies be there in the program, but we try to fill in these stall cycles by the hazard through instructions which are there in the program. But before that, we need to find out the dependencies of the flow of the program, and if we can accurately see all the dependencies, then we can obviously find out those instructions which are not dependent on each other, and this would mean that these instructions can be filled in those gaps in those stall cycles. And this is the prime way for doing it through compilers. And this was also there in the last slides that I gave you, and this is just a repetition of those things that we are going to do today. So this was about data dependence or true data dependence, but there is another type of dependence which we call as name dependence. So a name dependence is actually the use of the same name, and that name can be a register name or a memory location, right? So if two instructions use the same name but there is no flow of data in between them, then we say that these two are name dependent only, right? So they are not true data dependent but name dependent. So we say that two instructions are name dependent if instruction X that obviously precedes instruction Y in program order. Name dependence have two types: empty dependence and output dependence. So an empty dependence is going to occur when there are two instructions X and Y, where Y writes a result and X uses that result. Not that result, X uses that name, that memory location or register. So I'm going to give you an example. You can ask me any questions when you want. So a true dependence always has a flow of data, but when you're talking about name dependence, we are going to take two examples. Like we have an add instruction, say for example, and it's producing a result R1, but using R2 and R3 as well. And R2 is added with R3's contents to get R1. Now this is X. Let's say an instruction which is uh, preceding instruction Y, which is later in a program order. And we have another instruction subtract, which is producing a result R2 and R4. It's subtracting R4 and R5. You can easily see here there is no flow of data because subtract is not using R1 in any of its source registers. Okay, so this result is not. So in other words, we could say that subtract and add can happen together, right? So if they are not dependent, if they are not data dependent, then we said that okay, so they can have a different program order, but they are not true data dependent. But there's another type of dependency in between these two instructions, and that is the name dependence. So let's say if we run subtract before add somewhere here, what would be the result? So let's imagine that subtract is before add. So we are actually subtracting R4 with R5 and producing a result R2. Now, if subtract was before add, then add, since is using R2, is going to get that particular value of subtract, which is going to be wrong. So even though there is no true data dependence between these two instructions, but there is another type of dependency which we call as anti-dependence. Now we are calling that anti-dependence because if we are going to just flip these two instructions such that subtract is before add, then you can see that there would be there would be a two data dependence between subtract and add. There would because subtract is going to produce a result R2, and then add would be using R2, and then there actually there is no dependence right now, but there would be a new data dependence if you are going to flip these two. So we call that as an anti-dependence. There is not actually a dependence, but if you're going to flip if you're going to bring subtract before add, then there would be some kind of a dependence between add and subtract. Now this dependence is because they are using the same name R2. Actually you can really easily see here that R2 can be replaced with any other register, so it's not necessary that you are must to have used R2 in this place of subtract. You could have used R6 as well, and the only thing is that this subtract result would be used subsequently in some other instructions. So all those instructions need to be replaced also with R6. If you're going to change R2 with R6, then all those remaining instructions should also be replaced with R6. If you ensure this, then you can use any register. So there is an anti-dependence between these two instructions because they are using the same name. Otherwise, there is no flow of data. Is this thing clear? Is this thing clear? Because if this is clear, then I can move forward. So this is the first type, name dependence. So the program order is X is before Y, right? So if you see X before Y, you can see that Y does not have any true data dependence with X, right? Because there is no flow of data. But there is a name dependence, and that is an anti-dependence, because name dependence has got two types, an anti-dependence and an output dependence. So we see here an example of anti-dependence, and so let me just go through this definition here. An anti-dependence between instruction X and Y occurs when instruction Y, which is later in program order, writes a register or memory location that instruction X reads, right? So the earlier instruction is reading it, then the later one is producing the result, right? So actually when the later one is producing a result and earlier one has read that result, so there shouldn't be any problem here. But we are going to call that as anti-dependence, because if for example you change the program order, then there would be a true data dependence between them. So there is no dependencies right now. But if you're going to change the program order, because when you're talking about static scheduling or dynamic scheduling, there are going to be instructions which are going to run out of order, right? So there you are going to encounter such kind of problems. So anti-dependence means there is no true dependence, but if you're going to change the program order, there would be a dependence. So it's easier to find out anti-dependencies in the program as well by the same rule. Okay, then there is a second type of name dependence, which we call as output dependence. And output dependence is going to occur when both the instructions are going to write to the same output, right? So we see here an output dependence occurs when instruction X and instruction Y write the same register or memory location, right? So if let's have an example of output dependence. So for example, we have an instruction X and instruction Y, and X is add R1, and other registers could be anything, and say subtract again to R1, and other registers could be anything. So in this particular example, you're going to see again there is no flow of data. A flow occurs when a previous instruction writes to some register and the later one uses that register, right? So if the later one is not using that register, then this means there is no flow of data. So you can see there is no flow of data, but again use of same name by both of these instructions. So you can easily remove name dependence by changing the name. So this is not necessary that you are going to write to R1. You could have used another register. You could have used R4 instead, or R2 instead, or any other register. So if you have used any other register, you would have seen that these two instructions then become totally independent of each other, and then you can move them anywhere in the program order, right? So, but since they are both writing to the same register, now you are going to say them as output dependent. Okay. So so output dependence occurs when instruction Y write to the same register or memory location, right? So if in this example, when you are going to write to the same registers, you're going to ask why are we going to have two such instructions which are going to write to the same registers without doing anything. So this is just an example where you have shown two instructions X and Y, and I have missed some other instructions in between. So there could be some other instructions in between as well. Obviously some instruction after add which is using the value of R1, because if there is some result produced and some instruction is not using that result, then this instruction is of no use. So maybe there is some instruction between add and subtract which is using this result R1, but subsequently there is a subtract instruction which is producing again to R1. Now this is a problem because they are both using the same name. So if I'm going to change the name from R1 to R2, then there is no dependency between these two instructions, but I have to ensure that anywhere in the program where R1 was used is also replaced now with R2. Okay, is this in clear? Any questions here?
Yes, sir. Clear.
Okay, so
Excuse me, sir.
G,
So
Sir, your voice is breaking.
my voice is not clear. Is
No,
this
sir, there jerks are coming, but maybe I have some net issue, or uh, is same being experienced by all or only me?
yeah, can anyone else also tell? Iqbal
it's
Aziz is
fine. It's fine,
uh,
sir, for me.
okay, it's fine for you. Are other people experiencing these
Okay,
jerks?
sir. Let me check my let me check my connectivity. Let me check my.
Okay. Anyhow, this is recorded. So if you are experiencing any problem, you can view the recordings later, right? So yeah, maybe some issues with a few of you.
Sir, one thing more, sir. Apart from it, can you allow us the downloading of these videos? Because
Yeah,
sometimes
I
while
have.
listening, due to
Yeah,
buffering, video got stuck.
yeah, I tried that. You asked me before that as well. I tried that to look for those options in the meetings. There were two things when we were doing undergraduate classes online. We were actually uploading the videos, so we were recording everything offline, and then we were uploading those videos on Google platform. And there they had an option to allow downloads. There was an option to allow downloads, but these meet recordings, I was looking at that, they are not allowing any downloads. It's maybe an institutional policy, but I'm not getting any option for allowing downloads, so you can only view that on Google platform. This is only for meet recording, but previously when we were talking about those undergraduate classes, there we had an option to allow the students to download them, and students downloaded those recorded videos. But since this is pre-recorded by this recording is not happening at my end, this recording is happening at Google's end, so this all meeting is recorded at their end. So I'm not sure why they have not allowed any downloads. So I looked at that before as well, so it's not there. So
Okay, sir.
you can only view that on Chrome or Google's platform, other applications that run on that. Okay. Yeah. So
Thanks for the clarification, sir.
okay, thank you. So let's move on. So we have talked about derivative dependence and name dependence. So this is an example, and I've already told you this. Okay, so let's look at this example once more. So you can see here that R1 is utilized by R1 in this case. This is an example from the same 5 instruction code that we were discussing. So there was a store and add. So if you recall, okay, so we can have that again as well. But this is a store instruction which is using R1. So this is reading, and this is writing. So normally when you are writing to some register and the next instruction reads it, that's a two data dependence. But when you are reading it first and writing it later, then this is an example of anti-dependence. So we are going to say that store and that this add immediate instruction are anti-dependent on each other, right? So this is one example of anti-dependence. If you talk about output dependence, again, this example could be that both of them are writing to the same register, and this is an example of output dependence. Yes, as I mentioned, that output dependence and name dependence can be removed. Actually, name dependence, including anti-dependence and output dependence, can be removed if we do a register renaming. If you can rename the second register or the first register by some other register, then you are going to see that there is no more dependency in the program. Right. So this was the main thing that I was trying to bring you towards, and these data hazards can be written in a different way in the orders of reads and writes. So we have talked about dependency, and then there is another way to write those data hazards in the order of reads and writes. So there are three types of hazards: the raw hazards, the WoW hazards, and the war hazards. And this is something that I gave you in the last slides of multi-cycle pipeline, and there I was discussing about raw, war, and WoW hazards, and then later I realized that we have not discussed these in the class. So these initial slides were because for introducing these three hazards. So raw means write after read after read after write. Sorry, raw, read after write. Now, when you talk about read after write, so which one is coming earlier? So we are saying read after write. So which one is coming earlier?
So right.
Write is coming earlier, right? So we are saying read after write. So this means write should happen first. So whenever you are going to write to some register and later on read that register in some other instruction, so this can be an example of a raw hazard. This can result in a raw hazard. So if you are writing to a register and later on reading that register, this can be example of a raw hazard, right? Write after write means you're writing to the same register twice. So for example, you're writing one instruction is writing to a register, the other is writing also to that same register. This can be example of a write after write hazard. Then we have a write after read hazard. So read is happening first and write is happening later. So you are reading something in an early instruction, and then later on in the later instruction you're writing to that same register. So this is an example of a war hazard. So now you can easily relate these three hazards. So this is the true data dependence that we just discussed. So this is an example of true data dependence. This is an example of output dependence. And this was an example of entry dependence, right? So this is another way to discuss these data hazards in the order of reads and writes. Okay, so we sometimes call as true data. We can also have this as a raw hazard, right? So a raw hazard means that you can easily relate that raw means that read after writes. So those slides when we talk about a multi-cycle operation, those slides had these words of raw, war, and war hazard. And while I was discussing that in the last lecture, I realized that we have missed that. In this lecture, I have started with these details first. So all these details are here. So it's not very difficult because we have already discussed that. Y tries to read a source before X writes to it. So Y incorrectly gets the old value. This WoW hazard is like an output dependence. So Y tries to write an operand before it's written by X. Now these hazards, the raw, WoW, and war hazards are going to occur when you change the program order. Now you have a normal program order where some instructions are before other instructions. So X and Y. So if X is writing to some register and Y is reading that register, right? So this is okay. But if you change the program order, or somehow you want to find out, you want to try to have Y before X, then this is going to result in a raw hazard, right? So there is a true data dependence, and true data dependence is going to result in a raw hazard if you are going to have Y before X. Okay, so if Y goes before X, then this means that Y is going to not get the value of X. It should get the value of X, but if Y is done before X, then it's not going to get the value of X, but it's going to get an older value of R1, right? So this is the same thing written over here. Y tries to write an operand before it is written by Y tries to read a source before X writes to it. Uh, so y is going to get an incorrect value. This is going to happen when you are going to come to the next topic, which is scheduling of instruction. We will change the program order to make enhance the performance of the system. So here we have discussed all these three types of hazard. Then there is another type which is going to be called as a read after read, but this is not a hazard because you can read in any order. So if two read after read means you want to if some instruction reads the value of r1, uh, um, if some instruction reads the value of r1 and another instruction reads the value of r1, uh, so there is an add instruction, there is a subtract instruction. As long as this is not producing any result which is used by the second one, then this is an example of read after read. You are reading r1, then you are again reading r1. But this is not a hazard because now you can change the order of subtract. So reading of one value and another instruction reading another value at the same register, doesn't matter which happens first, right? So you can have subtract before add in this case. That's not a hazard, right? Okay, so now let's come to our main topic: how to exploit instructional parallelism, how to enhance extra instructional parallelism. So the first technique that we are going to look today is static scheduling. Static scheduling means that this is done at compile time. So the compiler is going to look at the code, is going to find out how many data hazards are there in the code. So for those data hazards, going to leave those stall cycles. Then the compiler is going to statically schedule the code. Statically schedule now means that it's going to rearrange the code so that it fill those stall cycles by instructions which are not dependent, right? So I hope you all get this point. So I'm going to skip this text over here. You can read that yourself. Let's come to an example. So this is an example where add is producing a result r1 and branch is using that result r1, right? So normally you're going to see that add and branch can go along without a hazard, without any data hazard, because add is going to update the value in execution stage, and branch and is going to compare the value in execution stage. Now, if you go with this assumption, then there is no problem. But remember, when we were talking about control hazard, we said that for branches, it's better we do things earlier, that is in decode stage. Now, in this example, we are going to assume that branch is going to compare these values in the decode stage. Now, I'm going to draw a short pipeline diagram over here. So, add is going to go through the fetch, decode, execute, memory, and write back, right? So this is for add, say. Branch is going to start a cycle later, which is going to be fetch, decode. I'm going to stop over here. Now, we say that in the decode stage, we are going to compare the value of R1 and R2. But in the same cycle, add is actually doing the execution, which is it's reducing the value of R1 by 8. Right, so it's actually adding immediate, and immediate value is -8, which means you are subtracting -8 from you are adding -8 to R1, which is actually subtracting 8 from R1. So this is happening in this cycle, and we need the value of R1 also in this cycle, which we said earlier that this is not going to be possible now. If you are going to do everything in decode stage for branch, you need to have a stall in between these two instructions. So actually, there should be a stall in between these two instructions. Okay. And then later on, through static scheduling, what we are going to do is we are going to fill in these stalls by some useful instructions. So compiler is going to first of all go through your code, find out how many stalls are required, and then try to fill in those stall cycles by. So this is an example of a data hazard stall due to data hazards, and the compiler is going to try to fill in these stalls. Right. So let's come to our main example now. So pipeline scheduling. This is our main topic: pipeline scheduling. How to do that scheduling. So let's say we have a program in which we need to add a scalar value, a constant, to all elements of an array, right? So, and this example has got 1,000 elements in X, and we need to add a constant or scalar value of S to all elements individually uh, of X one by one. Now, this program does that, and if you want to write a MIPS code for this program, it would be something like this. So I'm going to just quickly go through this code. So since this is an array which is in the memory, so what we are doing is, first of all, fetching the first element into F naught, right? Then we are going to add that value S to that and storing it in F4. Then we are going to store it again back to the same memory location from where we have fetched it, right? So then this is for one element. So we are going to repeat this now, repeat it 1,000 times. So for that, we are going to change our address, and changing address here means that we are decrementing the address. So it's a double precision number, so we are going to subtract 8. We could have added 8 as well, but in this array we have assumed that the first element is at the lowest address. So if this is at the highest address, so if this is 1,000, then our next one would be 992. The next one would be 986. 984. Right? So there should be a difference of 8 in between all of them, right? And so eventually you are going to come to 0. Okay? Or what you can say is it's not actually 1,000, but some value in R1, and we are going to subtract it by 8, and this last value, where whatever that value is, it's in R2. So whatever that value is, so it's in R2, and we are going to check when you are going to start subtracting 8. Actually, you are going through all these elements one by one, and when you want to stop, you want to just compare whether we have reached the value of R2 or not. Okay, so this is the last instruction, what's happening over here. So if both of them are equal, then you are going to stop your loop. If they are not equal, then you are going to continue. So this is how it's done, right? So this is easy here. It's nothing difficult. Now, this was the same code that we saw some cycles earlier, some slides earlier. So let's try to find out the dependencies. So what the compiler is going to do when it's going to look at this code, so this code is running in a loop. This is the first thing. Now, what the compiler is going to do, it's going to first of all find out how many stalls cycles are needed between an instruction which is producing a result and the instruction which is using it. So for that, we have a latency graph here, a latency chart here, which tells instruction producing result and instruction using result and how many cycles to wait for it. So for example, if there is a floating point operation and then there is another floating point operation which uses that result, so you have to wait for 3 cycles. Actually, this is from the same lecture where we were talking about multi-cycle operations. So multi-cycle operations in MIPS pipeline, where we said that for add, the latency is 3 cycles. So because add has got 4 stages, so that was the reason. If you can go through that previous slide, so that would be 3 cycles of wait. So if there is a floating point add and another floating point operation which is going to use that result, it has to wait for 3 cycles. So if there is a floating point add operation and then there is a store operation, so store is going to wait for 2 cycles. It doesn't need 3 cycles. The reason being, the store is going to need that result in the memory stage, not the execution stage. That's why 1 cycle has been reduced. And if there is a load instruction producing a result and a floating point instruction using that result, then this is called as a load use hazard. It's going to have a 1 cycle stall. If there is a load producing a result and store using that result, there won't be any stall cycle because store is going to use that in the memory stage. Okay, so having this in mind, And the example that we just saw earlier. So what we have done is going through the same chart. There was a load producing a result and add using that result F naught. Okay. So we go through this chart and see here the load producing a result, floating point operation using that result, one cycle stall, right? Add producing a result and store using that result. So according to this chart, we need two cycle stalls in between these two. Then the third instruction was store and the fourth one was add. Since these two are not dependent, two data dependent, there is no stall cycle between that. Add producing a result and branch using that result. So we have already discussed that in the previous slide that you need a single cycle stall because a branch is going to work in the decode stage, right? So if you go through that simple 5 instruction code, this is actually going to have the last instruction issued in the 9th cycle. So there are 4 stall cycles which the compiler needs to um, fill in with useful instruction. But since this is a loop, there are not more instructions in in this particular iteration. So what to do? Now the first thing that can happen is we need to find out dependencies. So we see here this is dependent. So add is dependent on load, store is dependent on add. So this means that you cannot change their order. You cannot have store at this place, right? So we need to fill in this stall cycle. So what we can do is this add dependent on this add immediate dependent on this floating point add. Is this thing dependent on this? Or is add dependent on store? Two data dependent? Come on. Is this add immediate dependent on floating point add or this store floating point store? Yes, anyone? Come on.
No, sir. Add is not dependent on the add.
Okay, so it's not dependent. So when it's not dependent, what you can do is you can move it here. Right? So this is the first thing that the compiler can do. So instead of writing this code in this way, the compiler is going to have the load and then the add immediate. But there is one thing more that is happening over here. Add immediate is producing a result R1, which is anti-dependent with store. So these two instructions are anti-dependent. Remember, it's not only about true data dependency. We have to check for anti-dependencies and output dependencies as well. So if there is an anti-dependence, again, you cannot move the code. Again, you cannot move that instruction. But then you can do another trick over here. What you can do is this instruction is updating the value of R1 and store is using that value of R1. Since you have subtracted 8 from R1 and you are doing that before the store instruction, what you can do is then later on in the store instruction, instead of adding it with 0, you can add it with 8. And this is going to nullify this effect. So if you're going to subtract 8 at this point, and then in the store instruction, what you're going to do is add 8 with R1. This is actually going to point to the same location which was 0 R1. Right?
Excuse me, sir.
G.
Sir, can you please explain the add immediate instruction?
Okay, add immediate instruction. What add immediate is going to do is it's it's going to add an immediate value. So what add immediate has important thing here is this should be a register and this should be an immediate value. An immediate value means that it's a constant or it's something that is provided as part of the instruction. So here what's happening is we are using R1 and R1 both over here because we need to put the result over here. Again, this is not necessary to be R1. This could be any register as well. But this is -8. -8 means that, for example, R1 has value of 1000 at this point, and you are adding -8 to it. So the new value for R1 would be then 992. Okay. So this is what add image is going to do. Okay. Now, when you have, if you want to, what's happening over here is we are loading from location, say 1000. So if you are if we are um, if we are loading from location 1000 and then we change the value in the very next instruction, and R1 was actually 1000, but now we have reduced 8 from it, so that R1 becomes now 992. Okay, but we need to store the value again in the 1000 location. So how to make 992 again 1000? So what we do is do another trick. So instead of using 0 with R1, we are using 8 with R1 or 992. So this would again become 1000, right? So this is the trick that is happening over here. So if you can do this, then this anti-dependence can be overcome, and then what you can do is shift this instruction right after load, right? So this is the thing that we have done. I'm going to show that in the next slide. Is this thing clear? So in the next slide, what we can do is we have moved this instruction right after load to remove that one stall cycle, and it not only removes one stall cycle, but it removes two stall cycles, because there was a stall between add and branch, and automatically there are many instructions between add and branch. So there should have been one instruction between add, and then there are actually now four instructions between add and branch. So that automatically helps that our cost. And then we have replaced that 0 with 8. So this is now going to be the same program. Instead of 4 stall cycles, now we are left with just 2 stall cycles. So automatically it has improved the performance. But again, we need to improve it further. We need to have less stalls cycles. We need to completely remove those stall cycles. So how can we do that? So then there is another technique. So this was the first technique, which was only pipeline scheduling. Pipeline scheduling means that the compiler is going to look for code and then it's going to rearrange it in such a way. Then we can have another technique which we are going to call as loop unrolling. Now in loop unrolling, what we do is we unroll the loop as many time as needed. Unrolling the loop means we are going to write the code, the body of the loop, as many time as required or as needed. So it just replicates the loop body multiple times, and we have to obviously adjust the loop termination. So this instruction, this code here, which was discussed in the last slide, which is working on 1000 elements, this can be unrolled if you are going to write this. So the main thing is this particular instruction, which is the body of the loop. If we can write this twice, if we can write this thing twice, which would mean that we are talking about xi, which is over here as well, and xi minus 1. Since we are starting with 999, so we are talking about 999 and 998. Okay, so 999 and 998 together in one loop. So one loop which is going to do two array elements together. Okay, so if you're going to do such a thing, then what you need to do is also update the update how I is going to be modified. So instead of subtracting 1 from I, we have to subtract 2 from I now, so that now it points to 997 and 996 in the next iteration. So this is an example of unrolling it. So I'm going to, yeah, this is unrolled by a factor of 2, and this is unrolled by a factor of 4. So you can see here we have written the loop body 4 times, I minus 1, 2, 3, and we have also adjusted the termination condition here. Now, what is the advantage of unrolling the loop? The advantage here is these iterations are independent of each other. So since every iteration is going to be translated to 5 MIPS, 3 MIPS, sorry, the loop body consisted of 3 main instructions. 2 of those were related to the termination condition, where one of them were add immediate and another one was branch. So the main body was load, add, and store. So these were 3 instructions. So what we need to do is replicate those 3 instructions twice or 4 times, and this is going to help us in getting more instructions that can fill in those stall cycles. I'm going to come to that. Let's unroll by a factor of 4. Now, this is the same program. What we have done is unrolled it by a factor of 4. So I'm going to just point out what are the 4 iterations here. These are the 4 iterations here. And just once we are going to do that add immediate and branch. Okay. So what you can see and observe over here is what we have done is the first one is talking about 0R1 and we are storing it to 0R1, right? Then obviously we are subtracting -8 in each iteration. So we have talked about -8 here and -8 here. Then further -16, -16, -24, -24. The last thing we have to update is to, since we have done 4 times, so we have to also update it to -32. Now, looking at this, you are not going to see that there is much of an advantage, because for every load and add there is a single stall at this place and 2 stalls at this place. So but there is no stall between load and store because these two are different instructions. So you can see there is no dependency between this load and this store. Now if I ask you about this load instruction here, and I ask you whether there is any dependence with this store or add or this load, you're going to say no. Why? Because we have used a different set of registers in all of these 4 expansions of that loop body. So instead of F0 and F4, we have used F6 and F8. Obviously F2 is going to remain the same because that's the same constant that we have to add in all of these 4 iterations. But instead of F0 and F4, we have used F6 and F8 over here, F10 and F12 over here, and F14 and F16 over here. This is going to ensure that we are using all different registers, so there is no need to worry about register renaming. So this load actually does not have any dependence with the store, nor with this add, nor with this load, which means that this load can come anywhere in between add and store, or anywhere in between load and add, wherever needed. Okay, so what is done in this slide is just unrolling, but simple unrolling is not enough. So again, there are many stall cycles. So what we are going to do is do pipeline scheduling with loop unrolling. Okay, that's the next topic here. So if you do pipeline scheduling with loop unrolling, your end result will be something like this. So what we have done is, since we had a stall, we needed a stall between load and its corresponding add. So what we did is brought in another instruction from another iteration, and we have placed it in between that, in between these 2 instructions, which is independent of these 2. And since we needed a stall between that particular add and its corresponding that particular load and its corresponding add, we actually have 3 more instructions between that, so that we don't need any further stalls. So likewise, what we have done is we have moved all the load instructions, and then we have all the add instructions, and then we have all the store instructions. So we can see here we have removed all those stall cycles. So except that there was one stall cycle between add immediate and branch, so we have moved that add immediate from this place to this place here and change it to -32. And since we have subtracted -32, so what we are doing is adding 32 to make it 0, adding 24 to make it -8, adding 16 to make it 16, and adding 8 to make it -24. Right? So this is how it's done, and now it's pointing to the same locations: -8, -16, -24. Okay. If you are going to do it this way, then you're going to see there are no stall cycles, because add and store has one stall cycle in between them. You already have 3 instructions. Add and its corresponding store should have 2 stall cycles. You have already 1, 2, 3, 4 instructions in between them. And this is true for all the iterations. So add is dependent, this store is dependent, this store is dependent on this store is dependent on this add. So all of them are going to different add. So this store is dependent on this add, and this store is dependent on this add, and this store is dependent on this add, and this store is dependent on this add. So actually for all of these there are three more instructions in between them. You actually needed just two stall cycles. So if you're going to see this code, this is going to run in as many cycles as there are instructions. So you're going to see that the last instruction is going to execute is going to start in the 14th cycle, and you have totally eliminated all the stall cycles due to data hazards. So this was a compiler technique to exposing ILP. So I'm going to repeat this. You can go through this if the unroll factor is not the multiple, if the loop iteration is not the multiple of unroll factor, what to do in this case. I'm going to just go through that. I'm coming to the summary. So what you are going to do is unroll the loop, find out those instructions which are independent, and then you are going to fill in those gaps, right? And this is going to obviously result in less less stall cycles. So a summary for whatever we have done up till now. So we have for this lecture, we have talked about compiler scheduling, which can remove stalls and speed up the code. The main thing is you need to find out dependencies in the code. So there can be three types of dependencies: the two data dependency, anti-dependence, and output dependence. There's another dependence which is control dependence, which I have not covered here yet. When you're talking about control dependence, it's actually a dependence of branches with other parts of the code, right? Okay, so now what is the disadvantage of static scheduling? Now static scheduling, first of all, is done at compile time. So many things are not known at compile time, and so you have to be a little cautious. So for example, there are two memory locations which are, so first of all, you cannot do anything about the memory locations because you don't know about those addresses. So at compile time, you don't know whether two addresses are actually the same memory locations or not. So that's one of the advantage or disadvantage. The second thing is whenever you're doing static scheduling, you are keeping one pipeline in mind. Like the one we have discussed in our slides is about the 5-stage pipeline, where we have one fetch stage, one decode, one execute, one memory, and write back. Now, if you change the pipeline, or if you're talking about multi-stage pipeline, then we already had that diagram with that table with us, which is going to tell us how many stall cycles do we need. But if you have a different pipeline, then you have to recompile the code, because that same code with those stall cycles are not going to work over there. So for every microarchitecture, you need a different code. That's the first disadvantage, right? So you have to write a different program. There should be a different compiler for, and the compiler should know about the internals of that particular processor. And as I've mentioned, that many dependencies are not known, like you don't know what that memory location is. So if there are two memory locations, one storing to a particular memory location, another instruction using that memory location, so you don't know whether they are the same memory locations or they are pointing to different memory locations. So many dependencies are not known. The third thing that can happen is, even with static scheduling, you have tried to remove all the stalls, but what would happen if that load resulted in a miss? So if there is a cache miss, and if there is a cache miss, you are going to lose a lot of cycles, right? So what are you going to do in those cycles? They are going to be a burden on you, and then they are going to reduce performance. You tried to remove all those stalls, but then it resulted in an unpredictable delay, and the first load that you encountered resulted in a miss. So if that's a miss, then the processor again has to stop. So what are you going to do? Nothing. So the processor cannot execute. So this is again one thing which a static scheduling cannot overcome. So these are the main disadvantages of static scheduling. So now we are going to come to our main topic, which is dynamic scheduling. So dynamic scheduling is about executing the instructions not at compile time, but looking at them at runtime. So you're going to write the code in whatever order you need, and they are going to execute. They are going to be fetched in that particular order. In other words, they are going to be issued and in that particular order, the program order, but they can run in a different order. They can run or they can execute out of order, right? So what we mean by out of order is if there is an instruction which is independent of the previous instruction, and if the previous instruction is waiting for some result, the next instruction, if it has got the operands with it, it should move on. It should not stop. Now let's take an example over here. These three instructions: add, multiply, and subtract. Now in a static scheduling algorithm, in a static scheduling option, what is going to happen is, if this is the order 1 2 3, then let's try to see these three instructions first. So add is producing a result, multiply is using that result. Multiply is producing result F4, but subtract is not using it. Neither subtract is using any result from add. So subtract is something which is not dependent on multiply and add, right? So since subtract is not dependent, but in a static scheduling algorithm, what will happen is, if the multiply is going to wait on add because it's using the result, so that result is not available up till this point. So if the multiply is waiting for add, anything after multiply also has to wait. So subtract also will have to wait, and it's not going to start its execution. But when you're talking about dynamic scheduling, what's going to happen is you are going to schedule the instruction in order, that is in every cycle. So first cycle, second cycle, third cycle. So when you come to that particular issue part, you're going to fetch that instruction. Then you're going to decode that instruction. In decoding, you're going to find out whether you have the required operands and that particular unit is empty or not. So if subtract unit is empty and you have F8 and F9 with you, then you are going to start your execution. If you're going to start your execution at this point, you're going to see you are going to end earlier than multiply. And if you're going to end earlier than multiply, you're going to see that their completion orders are also going to be out of order. So this instruction is going to complete earlier than the multiplication instruction. This is normal in dynamic scheduling, but then there are ways to ensure that the exceptions are always correct. So I'm going to come to those exception topic later. So today I'm going to talk about dynamic scheduling and what are the problems here. So I'm going to just again summarize. We were talking about static scheduling up till now. So in static scheduling, compiler is going to try to rearrange the code so that those stall cycles are removed. When you're talking about dynamic scheduling, there is no compiler, there is not a major work by the compiler. You don't need to reschedule the code. You don't need to shuffle those instructions. You can execute those instructions in the same program order, but then you are going to ensure that whenever at runtime, it's going to check the possibility of executing that instruction. So add, since its operands available, it can go through. But for multiply, its operands are not available because F1 value is not there. So it's going to stop multiply, right? But this does not mean that it's going to stop all the other instructions. It's still going to go on with other instructions. And if those instructions can continue, it's going to let them continue. That this is the difference between dynamic scheduling, and it's going to happen at runtime. So for that, obviously, you need some different hardware that can hold these instructions, that can know which instructions have their operands with them and which are pending, which have completed the results. So all of that is included under dynamic scheduling. So obviously, since you're not using compilers for that, you need hardware to maintain all the proper execution, the proper functionality of that program. So we are going to talk about those special hardware units that we need for dynamic scheduling in today's lecture and in the next lecture. Okay, so with dynamic scheduling, we allow the instructions to execute and complete out of order. This is what I have discussed. And then the second point is also what I have discussed. The instruction can begin execution as soon as its operands are available. And obviously, we need a special kind of hardware for that. This is the same type of example that we have earlier discussed, that if there is an instruction which is not dependent on earlier two instruction, then you should not let that instruction wait. So in order to start an instruction, the main thing that you have to check is whether there is going to be any structural hazard. That is, for example, if add and subtract are both you.
एक्सक्यूज मी सर,
G.
सर ये हमारे पास जो हम पीछे स्टैटिक देख रहे थे, देखिए वहां पर भी तो इंस्ट्रक्शन हमारे पास आउट ऑफ ऑर्डर ही परफॉर्म हो रहे थे, जो डिपेंडेंट नहीं थे उनको स्टॉल्स में रीअरेंज करके वो परफॉर्म हो रहे थे आउट ऑफ ऑर्डर.
If you are going to rearrange them, then you have changed the program order, right? You have changed the order in which the CPU sees that program. So you have written a program in a particular order, but then you have changed that order and brought another instruction somewhere from here to here or anyone. So the CPU is going to look at that order. So in static scheduling, the CPU is going to look at whatever order the CPU is going to look at. It's not going to change the execution of that order. So if there is an instruction which the CPU sees before, it's going to run that before, and it's going to execute that also before. So if this instruction is waiting for anything, all the others are also going to wait. Okay. And before that, compiler has changed the order and CPU is going to see that particular order. That's static scheduling. Here we are talking about that we are not changing any order. These three instructions go in the same way to the CPU, but during the execution, CPU sees that, okay, this can go, but second cannot go, but third can go. So it has automatically changed the order. Here the compiler has changed the order, and CPU sees the same order which the compiler has issued, and CPU is not going to change the order in any way. So nothing is going to happen at runtime. You're going to do it in whatever way the compiler has done. And if for any reason some miss happen or some cache miss happen and you have to wait for this, so all the instructions have to wait for it. Even though there are some instructions which are not dependent on this, but they are also going to wait for it. Here, what's going to happen is if one instruction cannot wait, is going to wait for another instruction, but the later ones are having their operands with them, they are going to continue. Okay, is this clear?
It means sir the main difference is static scheduling में हमारे पास इंस्ट्रक्शन आउट ऑफ ऑर्डर एग्जीक्यूट हो रहे होते हैं, बट इन डायनामिक हमारे पास एग्जीक्यूशन आउट ऑफ ऑर्डर हो रहा होता है.
इन स्टैटिक क्या बताया आपने? इन स्टैटिक के अंदर इंस्ट्रक्शन आउट ऑफ ऑर्डर,
स्टैटिक में हमारे पास इंस्ट्रक्शन आउट ऑफ ऑर्डर रीअरेंज हो रहे होते हैं और उसकी इंस्ट्रक्शंस के मुताबिक एग्जीक्यूशन हो रही होती है. बट डायनामिक में हमारे पास इंस्ट्रक्शन की ऑर्डर एज इट इज रहती है, जस्ट एग्जीक्यूशन में स्विचिंग होती है.
In one way you are right, but what I'm saying in static is you are not going to the CPU is not going to change the order. So if you have say let's take an example. So we have add, subtract, and say a load instruction over here, and then there was some other instruction like another add immediate over here, for example. Now before this is the program what you have written, right? Now before going to the CPU, the compiler is going to find out the stalls in between these instructions, and then when it sees that there is some stall in between, there is some stall cycles required because these two instructions cannot move together, the compiler is going to rearrange the code. And this is, say for example, the compiler rearranges the code like this, that add immediate comes before subtract and load, for example. Now compiler may or may not find suitable instruction to replace the stall. So for example, if there was some stall required at this point, so what the compiler has done is moved one instruction which is independent and moved it over here. Now the CPU is seeing the same order in which the compiler has issued it. If for some reason this add immediate cannot occur for some reason, right? Then all these instructions are also going to wait. When you're talking about dynamic scheduling, if this is your code, you're not going to change this code, and CPU is going to see the same code. During runtime, what is going to happen is add is going to go and then subtract. Since it's dependent on add because there was stall required, subtract is not going to be executed, but it's going to be issued. It's going to come into the CPU and you are going to fetch it, but you're not going to execute it. You are going to obviously put it somewhere in some structure, in some memory structure, where you're going to record it that this instruction should be the next instruction, but since the operands are not available, it's waiting for some operands. Then there is load instruction. Maybe this is also dependent, it's not going to work. But then there is an add immediate instruction. You're going to see that all of its operands are there, so you're going to execute this. Again, what the CPU did, what the compiler did was it had this add immediate earlier and it rearranged the code and CPU was seeing that code. Again, in the dynamic scheduling, you are going to see at runtime it's going to happen in the same way, except that, for example, if add immediate was waiting for something, all other instructions are going to wait here. But if, for example, add immediate was scheduled and now it has to wait, the other instruction below add immediate are still going to continue. Okay, so you're going to see that CPU is going to not change the program order. It's going to issue the instruction in the same way, but it can execute instruction in a different order. Execution means the actual working of that instruction. It can happen earlier than previous instructions. Okay, but here in static scheduling, you are going to rearrange the code. CPU sees the same code. It cannot change anything. If instruction has to wait, all the remaining have to wait. Right here, what's going to happen in dynamic scheduling, that there are different memories reserved, or different stations, that there are different hardware elements there which are going to keep record of which instructions are there, which are completing, which are executing, and you need to manage it in a different way. Right, so we are going to come to that, how to manage dynamic scheduling, because dynamic scheduling has to happen at runtime. So the first thing that we have to check is there shouldn't be any before moving that instruction to the next stage, which is the execution one. You have to check whether there is a structural hazard or not. So I was at this point. So for example, if add and subtract both use the add unit to add functional unit to add, and there is only a single add unit, then this means if it has been occupied by add, then subtract cannot execute, because that is going to create a structural hazard. So the first thing that you have to check is that there shouldn't be any structural hazards. The second thing you have to check is that all the data is available with it. So if the data is available and there is no structural hazard, you are going to continue with that instruction. Right? Okay. So that's the main thing in dynamic scheduling. I'm going to come to the different types of methods that have been implemented in the past and what is happening in the latest architectures. So are there any questions here?
No, sir. No.
Okay. Okay. So let's move on. So issue is in order, but execution can be out of order, and completion obviously can be also out of order. So the main advantage is here, you don't need an efficient compiler. You don't need a compiler which should need to know about the microarchitecture. You are writing the same program, and at runtime, that program is going to be fetched and executed. Those instructions are going to be executed whenever their operands are ready. Okay, and then the important thing here, when we were talking about memory addresses, so we said that at compile time we might not know about the memory locations. So we cannot say whether two instructions which are using the same address are actually the same addresses, or which two instructions which are using different register names are not pointing to the same address of memory. In dynamic scheduling, since we are doing it at runtime, we know all the dependencies, all the memory location addresses are known at this time. So we are at runtime, we would know whether they are pointing to the same memory location or not. And then it also allows the processor to tolerate unpredictable delay. So if there is a cache miss, then the remaining instructions are still going to continue, because if their operands are available, one of the instruction is waiting for a miss to fetch the data from main memory, but the other instructions are not, so they can continue. Now, the difficulty here is that this results in the possibility of war and WoW hazards. So if you are not going to implement it correctly, it can happen that you write to a register which is not read by any other of the previous instruction, a very thin chance, but there is a possibility. If your design is not very good, there is a possibility of war hazard, but very less chance, because you normally read before writing, and but there is a possibility of war hazard in out of order execution, because instruction later in order completing before time. So if there are two instructions which are writing to the same register, so since we are just checking about the structural hazard and the data structural hazards and the data hazards, we are not talking about the output dependencies. So if there are two instructions writing to the same register, where the later one is the first one is waiting for some result, but the later one can continue. So if this is going to continue, it's going to also complete. And if it's going to complete earlier, it's going to write to the register earlier. So if it's going to write the register earlier and later on you're going to write to R1 again from add, this is going to change the program order. So this is an example of a WoW hazard where you're going to write to the same register, but this write happens first, which should happen later, and this write happens later, which should happen first. So I'm going to come to those examples later. But there is a possibility of war and WoW hazard in if you're talking about dynamic scheduling. And then it complicates exceptions. Exceptions are interrupts. You can say software interrupts or hardware interrupts. So whenever there is an interrupt, normally what you do is you move to the service routine of that particular interrupt, and then you come back to your own program. So there can be interrupts from operating system level. We call them an exception as well. So if there are exceptions in your program and you are doing an out of order execution, then it complicates things, because an exception can occur from an instruction which is waiting, and later instructions have already completed. So what is going to be the status of the later instructions? Are you going to do them again? Because when you're talking about exceptions, you come back to your main program and do it again, or continue from that point. But since you have already executed those instructions ahead, there should be some record of which instructions have executed and which needs to be done again, right? And then there can be, because you're doing out of order, and the later instructions, if it produces an exception, how are you going to deal with that? So this is a little difficult thing in dynamic scheduling that complicates exception. Right, so there have been two different techniques in the past. Scoreboarding. These techniques are mainly from the 60s and 70s supercomputers, because obviously there were no desktop computers at that time, and the hardware was also a little difficult to fabricate on chip. So you just have had only the limited registers and things required. So if you want to implement dynamic scheduling, how to do that, and because those topics were related to all those supercomputers or fast performance computers, so these techniques are not new, but they have been implemented in very older supercomputers like CDC. So scoreboard was there, and Tomosolo's algorithm. So we are going to talk about Tomosolo's algorithm first, and then we are going to look at the variant of Tomosolo's algorithm, which is still used in recent architectures. So let's talk about Tomosolo's algorithm. So it was implemented in '66, 3 years after CDC. CDC was using scoreboarding, and so IBM 360/91 used Tomosolo's algorithm. So the main idea was that this processor had got just 4 floating point registers, and this is obviously going to give you an idea of uh, for 4 registers, it is hard to do register renaming. You obviously are going to use those same registers again and again. So if you're going to use those registers too frequently, you're going to see that there are too many name dependencies, and you cannot avoid those name dependencies, and that is obviously going to result in going to result in problems for the compiler. So there is again a little difficulty for doing static scheduling in here. So Robert Tomasolos tried to figure that out, how can we do that in hardware, right? So he came up with a scheme, obviously, of doing at register renaming that we have just discussed, to that if there are instructions which are not data dependent on each other, but they are using the same name, like in this example, there are two F6 over here for add and multiply. So this F6 here is actually pointing to this F6 over here, but this F6 has got nothing to do with this F6. Similarly with F8, there is an F8 over here and an F8 over here, but this F8 has got nothing to do with this F8, right? So if you can do this register renaming and remove those common registers, so F6 here is removed by S, and you have let this one to use F6, and F8 over here has been changed by T, anything, S and T can be replaced by anything. So you're going to see now there is no dependence in this code, and then you can move the instructions freely. So, but register renaming at hardware, how to do that? So for that, the hardware that we need in Tomaso's algorithm is called as a reservation station. Now this is a new thing here. So a reservation station is going to have different entries. It's going to store different things in each of these entries, like the instruction currently executing, the operands which are available and which are not available, and the reservation station number to which these results should be passed on to, right? The reservation station is going to fetch and buffer an operand as soon as it's available. And whenever there are pending instructions, it's also going to mention which instructions are waiting for, and it's against that instruction is going to mention the reservation station number from where it's going to get that result, the operands. And then there is a common data bus connecting all of this together. That common data bus is a come from bus, not a go to bus. Come from bus means that whenever result is calculated, is broadcast to all the reservation stations, and they are going to just check whether they need that result, and if they need it, they are going to keep that result. So many of those things are going to be clear when we come to an example. So this is an example, a typical example that we are going to go through. So this is something a little change over here. Now I'm going to first of all come to this floating point operation queues. This is our main, you can say, this is the queue which is going to hold the instructions, and this is going to be in order, right? So the program order. So you are going to have the instructions in program order. So the first instruction is going to come over here, the second one over here, the third one over here, and so on, right? You're not going to change this, but for every instruction, you are going to see which particular operation is required. So here we have shown two function units, an adder unit and a multiplier unit, and obviously there can be other units as well, but only a floating point adder and a floating point multiplier is shown. So if an instruction is add or an instruction is subtract, then it's going to go to the add unit. If an instruction is multiply or an instruction is divide, then it's going to go to the multiplier unit, right? So if your first instruction is add, it's going to go to this reservation station. Now this is an example of a reservation station. These are examples of reservation stations. So you can see here it's acting like it's something before the functional unit. So a reservation station is going to hold which instruction is that, which operands are available and which are pending, right? If both the operands are available, then it's going to give that instruction to the adder. The adder is going to produce a result and is going to then broadcast the result everywhere. So you can see here these blue lines here are the the bus which is connected to all the reservation stations. So it's connected to the same add reservation station, it's connected to the multiply reservation station, it's connected to the floating point registers, it's connected to the store reservation station. So anyone who needs that result is going to copy that result. Anyone who is not going to need it is going to discard that result, right? So I'm going to now come to that algorithm. So most of that is also going to be is also going to be cleared when we come to an example. So in Tomaso's algorithm, we are going to discuss about 3 stages. So we are going to break our instruction cycle in 3 stages. An issue stage where we are going to fetch instruction and check for structural hazards, right? So we are going to check for structural hazards, and if there are no structural hazards, we are going to then give that instruction to the reservation station. The execute stage, which is actually going to execute that instruction when its operands are available, and the third stage, which is the write result stage. So whenever that result is available, it's going to update the register. Then there is a common data bus in all of this. This bus is called as a come from bus, not a go to bus. So normally we have a go to bus which specifies the address where it wants to go. A come from bus tells where it has come from. So along with the data, you are going to send the reservation station number where it has come from, and anyone which is waiting for that particular reservation station is going to update itself. This is a difference between a come from and a go to bus. So it's actually going to broadcast its source, not the destination. Now within the reservation station, there are going to be different entries like the operation to be performed. There are going to be 2 different types of operand, because they are binary operands. So we are having operands which are V and Q. So V is going to store the value of source operand. If that value is available for the first operand, that would be stored in VJ. If the value is available for the second operand, it's going to be stored in VK, right? If both VJ and VK are available, then this means you can execute the instruction. If the value is not available for J, it would be stored in QJ. So what are you going to store? You're going to store the reservation station number. Because the value is not available, you're going to store the number from where you're going to get that value for the jth operand. And the same goes for the kth operand, right? So as I've said that much of that would be cleared when we come to an example. So let's just come to an example, because these things, when you're going to go through that slide, you're going to see, and you're going to it's going to be easy for you. Now let's come for an example. So what I'm going to show in this example is a set of instructions that we are going to execute one after another. So this is our program, and in order to maintain which cycle a particular instruction is issued, and when it's going to execute and when it has completed, we are going to maintain a table over here. This table is just for ourselves, so we are going to maintain it for ourselves, but it's not part of the algorithm. The main part of the algorithm is this reservation station here. So we have got 3 entries in add reservation station and 2 entries. So we have combined those 2 reservation stations as a single table over here. Then we have a list of registers that we have, and see, because all these instructions are updating a floating point register, so we are going to maintain which of these instructions are actually which of these instructions have actually updated those registers, and which are waiting for any particular results. And this is a reservation station for load. Whenever there is a load instruction, you are just going to mention the address of that particular load where it's going to load from memory. Okay, so now let's start. And before starting, let's also note down that for every load we need 2 cycles. So we are assuming that load's latency is 2 cycles. That is, whenever load is going to execute, it's going to take 2 cycles to execute. And add is also going to take 2 cycles, multiply is going to take 10 cycles to execute, and divide is going to take 40 cycles to execute. Execution means the main part when you're going to actually run that instruction. So it's excluding the fetch part and the issue stage and the write stage. So this is just the latencies for the execute 2, 2, 10, and 40, because these are the only instructions in our example, right? Okay, so let's start. So let's talk about cycle number 1. So in the coming slides, I'll be just moving on with different cycles, right? So this is our cycle number 1. Now what is going to happen is we are going to issue in the first instruction in the first. So this instruction is issued in the first cycle, right? So as I mentioned that this table is for our own convenience. It's not part of the algorithm. The main thing is that if it's a load instruction, it goes to the loads reservation station. So load reservation station also has got 3 entries here. So because all of them were empty, so we just used any one of them. So we have used the first entry and its name is load 1. This is the name of that particular entry, the reservation station name, load 1. And against that, we have written that it's busy now because it has been occupied. And what that load is going to do, it's going to use the value of R2 plus 34. Now 34 is part of the instruction, is already there. R2, since it's an integer register, we are assuming that all those integer register values are available already there because we are not updating those. So both of these register values are there. So 34 plus R2. So what's going to happen is you're going to fetch the value of R2. Say the value of R2 is 2000. So that value 2000 plus 34 is going to be written over here. So that's the address, the physical address. So 32 plus 2000 will be 2034. So 2034 is going to be placed over here. So you're not going to place 34 plus R2 over here. You're going to place the actual value over here in this reservation station because you know the value of R2. Okay, so if it's there, you can directly write the actual address over here. But that's not the execution part. The execution part of load is actually to load it from memory. Okay. Now, once it has been done, then you can get the data. So this is according to issue part. So you're going to load the address 2034 over here and store it over here. Okay. So this is about the first cycle. So we are going to issue it over here, right? And the other thing that we are going to do is we are going to record that F6 would be updated by load 1. Now you can see here that we are maintaining that which register is going to be updated with the particular. So if there is a reservation station name over here, this means that that value is going to be uploaded or updated by some reservation station. So we have placed the name of that reservation station, load 1, against F6 to indicate us that if anyone needs to get the value of access, then it should get this value from load 1, because this value of F6 is not there now in actually that register. It's there in load 1. So whenever load 1 is going to update itself, then you can get that value. Okay. So anyone in this code now, if it's using F6, it's going to get this value from load 1, which is this reservation station. Now let's continue further. Let's go to the second cycle. Is this thing clear till now? So this is our first cycle. In the first cycle, what we did is we occupied one of the entries of the reservation station, and we also updated our register that this register content is going to come from load 1 reservation station. Okay, if this thing clear? If it is, then I can move forward. Let's go to cycle number 2. Now in the second cycle, we have issued the second load. Okay, and because there are reservation station entries empty, so we have occupied the second load 2 reservation station. Now you can do it yourself. Whatever the value of R3 is plus 45 is going to be placed over here. That's the address part. Because the load reservation station have got just 2 entries, the address part and the busy part here, to indicate whether that particular entry is occupied or it's not occupied. And because it's updating F2, so what we do is against F2 we have mentioned the reservation station name load 2. Okay, so anyone who's going to need F2 later on is going to update itself not from F2, but from load 2 now on. Okay, now we come to our main instruction, which is the multiply instruction. So these are three things that we have done in the second cycle. Okay, is this thing clear? Now let's move on to the third cycle. So before moving on to the third cycle, let me just ask you people, what do you expect is going to happen in the third cycle? So we can do it over here. So in the third cycle, the multiply instruction would be executed, right? Okay. And since we said that load instruction is going to take 2 cycles, so our first load started in cycle number 1. So by that time, in the third cycle, this instruction should have completed the execution, right? Because the operand, the address was there. So we started in the first cycle. It takes 2 cycles. So by the end of third cycle, load 1 would have been completed. But once it's going to complete, then it's going to broadcast this result. So in the fourth cycle, then you're going to see anyone waiting for load 1 is going to get this result. What else is there? So in the multiply instruction, because this is a new instruction, it's going to occupy multiply a reservation station, right? And then we are talking about F2 and F4. So we are going to see which value is available. So F4 is available because there is no reservation station name against it, but F2 has a reservation station name against it. So we have Vj and Vk for values which are available. So if we occupy this multiply, then because F4 is the kth operand, so against Vk we are going to write the value of F4, whatever that value is, whatever that value is. So we have this value, but against Vj, because we don't have this value, it's going to come from load 2. So if the value is not available, we update the Qks and Qjs. So against that Qj, we are going to write load 2, right? So this is what is going to happen in the third cycle. Okay, so let's see. Let's move on to third cycle. So what has happened over here is we have issued multiplication instruction. We have occupied the reservation station for the multiplication, because multiplication instruction reservation station can have both multiplication and division. So the operation is multiplication. The value of F4, the value of F4 is with us. So whatever the value is, it's going to be read and it's going to be placed over here. So we are actually going to fetch that value and put it over here. So if that F4 changes afterwards, it's not important for us anymore because we have taken that value, right? So if anyone updates it later on, it's okay because we have taken that value and we have stored it over here. So multiplication reservation station, once it gets that value, the multiplication unit, functional unit is going to operate on this value. So we are going to load this value over here, and for that other operand, the F2 one, which was not with us, so we have against that operand we have written load 2. So whenever that value is going to be available, then we are going to start this multiplication operation. If that value is not available, we are going to put that in on pending state. So it's still going to be over here, but it's going to be in pending, and we cannot start this multiplication operation. So we have issued it, but we cannot execute it. The third thing that we have done is, since this multiplication is going to update F0, so against F0 we are going to write the reservation station name where that value is going to come from. So we have written here F0, right? And as I mentioned earlier, you can see here that load instruction is going to take 2 cycles to complete. So this load operation has completed its execution at the end of third cycle. Now in the fourth cycle, it can write its result. So it's going to broadcast its result in the fourth cycle. But since we have not started fourth cycle yet, so my question is, load 1 is going to complete. So is anyone waiting for load 1? So currently there is no instruction waiting for load 1 except for F6, which is a register. So you are going to update the register. So now F6 is going to be updated with the value of load 1, right? So now let's come to the fourth cycle. So if there are any questions, you can just stop me. I'm going to just continue on with these
Sir, kindly, due to electricity disruption, I couldn't listen, this third cycle, this F0 multiplied. Can you
Okay,
repeat this again? Thank you,
okay.
sir.
I'm going to do it again. So what's happening in the third cycle? So this was our second cycle. Now I'm going to come to the third cycle. Now we are going to execute the third cycle. We are going to issue the third cycle. So the first thing that we did is we issued the third cycle, third instruction in the third cycle. Then since this instruction was multiplication instruction, it has to occupy the multiplication unit, multiplication reservation station. So we occupied one of the multiplication reservation station, made its status to yes, busy status to yes, and then against the operation we have written multiplication, because multiplication can have both multiplication and division. Now we are going to see which operands are with us and which operands are needed. So we see here F2 and F4 are the two operands required, and against the register statuses, we can see F2 is mentioning a reservation station name, but F4 is not mentioning any name over here, which would mean that F4 is available. That value is actual in its register. So this means that this operand is available, but F2 is not available yet. That result has to be fetched from load 2 whenever the load 2 is going to give us. So one operand is with us. So the one which is the value, so V for value. So if any value is with us, so Vj, Vk. So since this is the kth operand, against that kth operand, we have fetched the value of F4. So we are actually going to take that value, read that value F4, and put that value over here. So whatever that value is. So for example, if that value is 1000, it's going to be over here. If that value is 1000 and say 1000.54, because we are talking about floating point numbers, they can have fractional part as well. So whatever that value is, it's going to be placed in this point, the Vk part, right? But the jth one is Qj. So again, you can see you can either have Vj or Vk together, or you can have Vj or Qk, or you can have Vk or Qj. But you can never have Vj and Qj together, because both of them are jth operand. So you cannot. So for one of them is for the value part, the other one is for which is not known yet, which is pending. So so you cannot have both of them available to, because they are both the jth operand. So you cannot have the value and as well as the reservation station name for that. So that's not possible. So the only combination of j with k or k with j, or j both the values are available or both values are not available, right? So in this case, one of the value was available, so we have updated that value. But for the second one, that value is not available. Against that, there was a reservation station name over here, so we updated with that reservation station name from where that value is going to be updated. So Qj, against Qj, we have written load 2. The third thing that we have done is, since it's going to update F0, so we are going to put that against F0, we are going to put that reservation station name mult1. Right, so these are three things that are happening over here.
Sir, Vj and Qj, can we store this load 2 value in Vj as well?
No, Vj means that value for the jth operand is with you. Qj means that value for the jth operand is not with you. Right, so you cannot have both of these states together, that you have that value and you don't have that value. That is not possible. Right, so either you can have both values for j and k, this is possible, or you can have both a value for one of them and the kth is not there, or you can have value for k but j is not there, or you can have both values not available, right? Where both of them are not available, but you cannot have that you have a value and you don't have that value. That's not possible. Okay, so let's move on to the fourth cycle. So no one is waiting for load 1, so except F6 would be updated. So let's move on to the fourth cycle. So in the fourth cycle, you can see here that the first instruction completed. Okay, so it's going to broadcast its result now, and when it broadcasts its result, so it along with that result is also going to broadcast load 1. So anyone waiting for load 1 is going to check for itself. Anyone waiting for load 1 is going to update it, like F6 has updated it. So this is written as memory address 1, MA1 for short. So address 1, because it was the first address, so memory of for the first address, whatever that value is, it's going to be placed over here. So it's not going to be MA1 written over here, but it's going to be the value, whatever value has come from the memory. So that's going to be broadcast. Anyone waiting for it is going to update it. So F6 is going to be updated for that. Right. In the fourth cycle, we have started a new instruction, subtract, right? And since subtract is part of add and subtract reservation station, so we are going to have one entry of that reservation station, whose name is add one, F6 and F2. So we are going to look over here now. Since F6 has got the value right now, so that value is with us, but F2's value is not with us. So we are going to write the F6 because that is the jth element. So we are going to put the F6 value with the whatever value that has been broadcast and is currently there. But the value F2 is not there. So that value is going to again be updated with the reservation station number load 2, right? And that is stored as load 2. Okay. Now, since this is the fourth cycle, so accordingly, F8 would be updated by the reservation station or add one. So this is the fourth cycle, and we know that at this point of time, load 2 is also going to complete its result. So by the end of fourth cycle, it's going to broadcast the result. So is there anyone waiting for load 2? So we can see here mult1, the multiply operation. The multiply operation is waiting for load 2, and the add is also waiting for load 2. Now let's see what's going to happen. When in the fifth cycle, you're going to broadcast load 2, both these reservation stations are going to start their operation simultaneously, right? So what will happen is when in the next cycle, this load 2 is going to broadcast a result because it takes 2 cycles, and since started second cycle, it's going to finish the fourth cycle. So now it's going to broadcast the result. When it's going to broadcast the result, it's also going to say it's coming from load 2. So anyone who is waiting for load 2 is going to update itself. When it's going to update itself, it's not going to write it over here. It's going to write the value in its kth or the jth part. So when these two instructions will have their v values available with them, they can now go on to their actual functional unit and start their operation. And then both the add and the multiply are going to start the same time. Okay. Actually, multiply and subtract were one after another, but since both their operands are now available at the same time, they both can start at the same time because they are going to different functional units, right? So let's start with the cycle number 5. So what's going to happen over here? The main thing is we are going to execute another instruction, divide instruction, which is going to occupy another reservation station. But the main thing here was load 2. So both these instructions, add and multiply, are going to execute simultaneously. And you're going to see here that we have again mentioned another thing for our own ease, the time which is it's going to take to complete. So subtract is going to take 2 cycles, but multiply is going to take 10 cycles to complete. So we are going to count down the counter from this point. So we have written the counter values over here, the values over here of how many cycles are needed for our own ease to see when is this instruction going to complete. But since both of them have got their data with them now, so both of them can now start their executions, right? So in the fifth cycle, the main thing that happened was that we have issued another instruction. We reserved mult2 to with that, since it's going to update F10. So F10 is going to get now mult2, right? What other thing has happened over here is since load 2 was say add 1 and mult1 were waiting for the both of them, and since it was updating F2, so F2 is now going to be updated as well, right? Okay, now let's move on to cycle number 6. Is this thing clear now? So you can do it yourself now. What's going to happen in cycle number 6? We are going to issue add. Okay, add is going to take another reservation station, F8 and F2. So you're going to look over here. F2 is available, but F8 is not available. So F8 against F8, which is J. So QJ is going to have add 1. So it's going to wait for add 1. But VK can have its value because F2 is now available, right? So I'm going to move on to cycle number 6. Right, so this is what is going to happen. Cycle number 6, we have issued another instruction add. It has occupied a reservation station, and like we said that one of the values available, other is going to be the reservation station name over here, add one. So it's going to wait for that. So since these are the 6 instructions in our program, so we are going to see when are they going to complete. Along with those instructions, we have mentioned a timer over here. So that's the only thing that's happening over here. And since it's updating F6, so against F6, now we are going to write add2. So anyone who's going to use add2 later on is now going to refer to, anyone who's going to use F6 later on is now going to refer to add2 for the value of F6. Okay, so now let's move on to cycle number 7. Nothing more over here. So since there are no more instructions mentioned in our program, so we are just going to continue with these cycles to see what's going to happen. So we are going to see here that after one more cycle, the first subtract in cycle number 7, the first subtract is going to complete now, right? So this is the completion time, because it's going to take, if it started at 4, it's going to take 2 cycles here. So it was issued in 4, but it actually started in the 5th cycle, and now in the 7th cycle it has completed. So anyone waiting for add 1 now? So we can see over here, yes, add 2 is waiting for add 1. So add 2 can now start in the next cycle, in cycle number 8. So let's move on to cycle number 8. So the subtract has completed in cycle number 8 and updated its value of F8, and add2 was waiting. So now the count of add2 has also started. So the multiplication is counting down, but add can now start because add has both its operands available with that. So what's going to happen in cycle number 9? Nothing more except that we are going to decrease those counter values, and cycle number 10 we are going to further decrease those counter values. Now add has completed. Now when add has completed, anyone waiting for add 2? No, no one is waiting for add 2 except that it's going to update F6. So it's going to update F6. So now there are 4 more cycles required for completion of mult1. So I'm just going to go and go on with these cycles, 12, 13, 14, and then in the 15th cycle you're going to see that multiplication operation has completed. So anyone who's waiting for mult1, yes, division was waiting for mult1. So now division can start. So in the next cycle now division can start, because then it's going to have both its operand available with it. So but because division is going to take 40 cycles, so we are not going to go and continue on this for 40 cycles. So we are going to skip 40 cycles and come to 56. So in 56 cycle division is going to complete, and then in the 57th cycle this is also going to finish, right? So what was the main thing in all of this? The main thing here was we have for our own compiled a table which is going to show us when is the instruction going to be issued, when is it going to execute, when is it going to complete. So you can see here the issue is in order. 1, 2, 3, 4, 5, 6. It's in order. The completion is out of order. So 3 and 4 was in order, but 15, 7, 56, 10 all out of order. So the completion is out of order. Likewise, the writing of result is also out of order. 4, 5, 16, 8, 57, 11. So you are seeing here the instructions later in order, completing earlier. So both of these are completing before the multiply and divide, right? So this is the main advantage of dynamic scheduling, that you can have execution out of order and you can complete out of order. Now this last part here, completing out of order, is a little problematic part which we are going to cover in the next class and not this one. Okay, so there is a small applet, Java applet available at this link that I've mentioned over here, where you can write your own code. You can write couple of 6 instructions here and give different register names and try to see how they are moving through in every cycle. That you can do. It's easy here. right? So you can change the register values, you can see what is happening at every, you can change the latencies as well. So this is a good program, a small program that you can use to see how this dynamic scheduling is going to work for using Tomasol's algorithm. Right. So there is another example that I have to continue over here because we have got 10 more minutes, and yeah, so this is part of the same Tomaso's algorithm. Now this example has a loop, and this is example is going to show what's going to happen in a loop, what's going to happen when you encounter a loop. So for loop, obviously we have to assume that either we are going to jump or we are not going to jump in a branch instruction. So here we are going to assume that it's going to be taken branches, so we are going to come back to load every time. So we are assuming that this branch is going to be a taken branch, and if this branch is a taken branch, then what is going to happen? So now we are going to assume instead of 10 cycles of multiply, let's take for 4 cycles of multiply. And we are also going to assume that the first load is going to take 8 clock cycles because it resulted in the cache miss. But the second load, because it's part of the same block, it's going to take just 1 clock cycle. Okay. So our first load is going to take 8 clock cycle, but our next load is going to take just 1 clock cycle because that would be a hit. Now these are assumptions before we go for the program. And branches are predicted as taken, right? And for clarity, we are going to show only the first 3 instructions, which are the floating point instructions in our program. And assume that these 2 instructions are also issued, but we are not going to show them in our structure over here that we are going to build for the reservation stations. Okay, so let's start. Now this is the second example, which has a loop. Okay, so this is cycle number 0. So in cycle number 0, this is the basic structure that we are shown. The cycle value would be shown over here and from the next slide. And these are the iterations that we are going to show, but this does not mean that it's going to execute in the 4th cycle. In the 4th cycle, we are going to execute the subtract, and in the 5th cycle, the branch. Then the 6th cycle, we are going to come back to the load instruction. Okay, so let's start. The only thing different here is because of store instruction, we have introduced a store reservation station as well. Now in a store reservation station, there is an extra entry, which is the reservation station name from where you are going to get the value of store. Because for load, you were getting the value from memory, so you only needed an address which was already there. But in store, you need an address as well as you need a value. So that value can come from a reservation station. So there is another entry over here which can mention the reservation station name against the store. Okay. And this is our main program, and the iterations are shown over here. So let's start. Cycle number 1. So I'm just going to go through that quickly now because you have already gone through that one example. So cycle number 1, load has been issued. You have occupied 1 reservation for load. Because the value of R1 is 80, so we have taken the value of R1 as 80. So 0 plus 80 would be 80. So the address is now 80, right? Since it's updating F0, so against F0, we have written load 1. Everything clear, right? Let's move on. Cycle number 2. Remember that we have said that this load is going to result in a miss, and it's going to take 8 cycles for it to come to get the result. But the second load is going to be a hit. It's going to take just 1 more cycle. So after 8, it's going to complete in 9 cycles. So the second load is not going to take 8 further cycles. It's going to complete in 9 cycle, right? Okay, so let's start. So in the second cycle, the multiplication instruction. So we have reserved the multiplication instruction is updating F4. So against F4, you have written mult1. And yeah, so we have F2 and F0 and F2. So F0 is coming from load 1, but F2 is there. So F2 is the kth operand. So kth operand is there, but the jth operand F0 load 1, everything as in the previous example, right? There's a lot of distortion. Should I go slow, or you are getting some problems in your connection? Yes, is are the other students also observing this?
Oh, sir, it's fine for me.
Okay, it's fine for the remaining one. Maybe there are some issues with the connections for some students. Okay, so because this is the last example that we have, so I'm going to just complete that here. Um, I'm going to get a little slower, but we have just few minutes, and it's not very difficult. I just have to show one point over here. What's happening when you are using the same name? So that's the main point that I want to show over here, because you can see in the same iterations, the code body does not change. So all those registers are the same. So my main point that I want to show in this example is what's going to happen when some of the instructions were using F naught, and here also F naught, but later on that F naught was changed. So what about these instructions which have not completed? How are they going to go through? Okay, so I'm going to go to the third cycle. In the third cycle, we are going to issue the store, and likewise you can see in the store instruction is going to put the value F4 in the memory location 0 R1. So R1 was 80, so 80 is the address. F4 value is going to come from mult1, so it's against the store reservation station it has written mult1. So everything fine till these three cycles. What about the fourth one? So in the fourth one, we are not going to issue load, but we are going to have subtract over here because that's our fourth instruction. And the fifth one, we are going to have branch. So I'm going to just go through that fourth and fifth. So fourth and fifth, right? Now we are going to have the load. So in the fourth and fifth, and now in the sixth one, we are going to have the load. So in the sixth one, we are going to occupy another reservation station for load. The first one hasn't completed its task yet till the 8th cycle. So now you can see the main thing that's happened. So before that, F naught was updated to F4.
Hello, excuse me, sir.
मेरे ख्याल से सर की कनेक्शन डीसी हो गया है मे बी.
Okay, students, sorry for the interruption. This was from my part. My connection got lost. Uh, just 1 minute. So today, because there was an interruption in at NAD, so I couldn't manage it from NAD. So today I'm doing it from my home. So that's why maybe the connection is not that fast as there at NAD. So that's why maybe some people are having a little problem. Um, yeah, so I was in cycle number 6. I'm going to do that again, and then we are going to just go through that and complete that. So in cycle number 6, we were talking about F naught and F naught being produced by two different instructions. So what's going to happen is when you're going to come to this load, this F naught is automatically going to go to load 2. This is the register renaming that I was talking about. So any instruction later on which is going to use F naught, it's not going to point to the previous F naught, is going to point to the later one, right? So let's go on to the next one. In the seventh instruction, mult1 is going to be issued, and then
Excuse me, sir.
G.
Sir, but what about the load 1? It was pointing to the load 1 before.
Yeah, it was F naught was pointing to load 1, but now F naught is going to point to load 2 because it's going to be updated by this one here. So you can see here F naught is written over here, and it's written over here, and it's used over here, and it's used over here. So this multiplier should use this F naught, and this multiplier should use this F naught. So when we were over here in the second cycle, that F naught was pointing to load 1. So the multiply instruction was using load 1. But then now we have moved to the 7th cycle. This multiplication instruction should use this F naught, so which was produced by load 2. So now you can see here, because you have updated F naught, now the second multiply instruction is using load 2. So you can see automatically they are using the right values. They are going to use the right value whenever that value is available. So whenever load 2 is going to propagate its value, mult 2 is going to update itself, not mult 1. Whenever load 1 is going to propagate its value, only mult 1 is going to update itself, not mult 2. Right? So this is the main thing about register renaming. So since we are now completed 9 classes, 9 o'clock we have completed a lecture. So I'm going to leave that in the next slides for you to go through. It's not very difficult. You can just go through these slides and see how they are
Excuse me,
changing.
sir. But sir, in previous example, we were taking the value from the register, but now the register headache is removed.
No, we are still taking it from the register. The main thing is, before coming to that register, we are just seeing whether that up till now, until the 5th cycle, F naught was updated by load 1, right? Now in the 6th cycle, what's going to happen is you are issuing another instruction, which is load, and you are going to occupy another reservation station. And since this instruction is updating load, this instruction is updating F naught. So what against F naught, instead of writing it load 1, because up till this point, anyone using F naught would have used load 1 in its place. But afterwards, since this instruction has come, which is going to update F naught, we are also going to update who is going to update F naught, and instead of load 1, we are going to write load 2. So after this point, anyone who is going to use F naught is going to take load 2 instead of load 1, right? So in the 6th cycle, we see here we are going to take update that with load 2. So in the 7th cycle, where we needed load F naught, we are going to update and put that load 2 over here.
Okay, sir, but it means that the reservation station will directly take the value of load 1 from the common bus.
Yeah. So that comes in the 9th cycle, when we said that this result is going to complete. So in 8 cycle, after 8 cycles is going to complete. So now in the 10th cycle is going to update. So anyone who's going to wait for load 1 is going to update it. So this multiplication instruction is going to now start, and in the very next cycle, this load instruction is going to also start. And so these two multiplication instructions can go on one after another. So this is an example that you can do it yourself as well. So the remaining slides I'm going to upload that on the classroom. You can go through that yourself. It's very easy. So in this example, it's shown how these instructions are automatically get a register renaming. So you're going to see that instead of so all of them are using F naught, but they are using the correct F naught, because whenever you are using it, you are not pointing to F naught, rather you are pointing to the reservation station name. So when you're talking about the reservation station name, you are going to change those names whenever there is a new reference to that F naught. So when you change the name, anyone using that name is going to update itself with the correct name, and this is how it's going to happen. Right? So I'm going to stop over here because it's the time is over. So If there are further questions, you can ask me in the next class. I'm going to stop the recording over here. So like previous cases, you just write your, so let me see, 1 2 3 4 5 6 7, all of you are present. Okay, so that's okay. So all of you are present over here, no need to write your roll numbers. Okay, thank you all. Right, so I'm going to stop it now. Thank you all. Okay, one more thing before you leave. The schedule has been announced for the exams. I'm not sure if they are still online or they are on site, but our paper is the first paper, that is on Monday. So we are going to have our last class, and there is not much of a gap. So we are going to have our last class maybe on 12th October, and then we are going to have, or maybe that last class is on 7th October. I don't remember, but the paper is on 12th October. Sorry, the paper is on 12th October. So this is one thing that you have to see, that yeah, our last class is on 8th October and the paper is on 12th October on Monday, right? So we have got 2 more lectures now left. I'm going to take the next one on the 1st October, and the next one on 8th September, and your final paper would be on inshallah 12th October, right? So you should be clear for that.
Sir, can we extend this final exam date to, instead of 12th October, in 19th
uh,
October? Is
I'm
it
not
possible, sir?
I'm not sure. I'm not sure about
Yes, sir,
that.
we are requesting about that.
I'm not sure about that. I can talk about that, but since that schedule has been announced, um let's see. Let's see if we can have anything different over there, right? So
But
At
sir, if
least,
possible, please kindly extend the date of this course.
um, yeah, okay. I'll try to talk, but I'm not sure about that. If they have got a fixed time, then I cannot do anything about that. But if they are leaving it to the teacher, then maybe I can do that. It all depends on if it's an online class or if it's a fixed schedule. I'm not sure about that. Okay.
okay, sir.
Okay. Thank you all then.
Thank you, sir.
Thank you.
Wow.